Welcome students to MOOC series of lectures on non-parametric statistical inference. This is lecture number 5. As I said at the end of the last class that in this class we shall study some mathematical results on linear rank statistics. So, what is linear rank statistics? It is a particular form of non-parametric test statistic which is used especially for testing a hypothesis involving two independent samples drawn from two different populations. So, consider one population from which we are drawing a sample x, there is another population from which we are drawing a sample y, and we want to compare these two samples to understand the behavior or the properties of these two populations. We have already seen some applications of linear rank statistics for various tests. In particular, you remember that we have discussed Wilcoxon rank sum test to compare the medians of x and y. Also, we have done Moore's test, Freud-Ansari test and David Burton's test. They also have use of linear rank statistic. So, if we remember, the linear rank statistic is of the form T n z is equal to sigma a I z I, where z I is an indicator variable. In all our examples, we typically looked at the z I value is equal to 1 for x and z I value is equal to 0 for y. Therefore, if we have 1 0 1 1 0 0 1, that means there are 7 observations, of which 4 are from x and 3 are from y, and not only that, in the sorted order they look like this. Therefore, z vector will look like 1 0 1 1 0 0 1. Now, what is a I? A I is a coefficient. Depending upon the nature of the test, we will use different a I's, as we will see later or we have already seen. Therefore, T n z is equal to the dot product of a vector with z written as a column. For this course, we shall restrict ourselves only to those linear rank statistics which are particularly sensitive for differences in location, that is median, and only in scale, that is spread. The assumption is that we have taken two independent random samples x1, x2, xm from one population, y1, y2, yn from another population, and essentially we want to see that the corresponding cumulative distribution functions, that is fx and fy, are same or not. That is what we want to test. So, samples are taken like that from the fx and fy distribution, only important assumption that they are continuous. And as I said, under the null hypothesis, we want to test whether they have the same distribution, that is fxx is equal to fyx is equal to fx, which is unknown for all x belonging to R. And to test this, we use the ordered arrangement of the combined sample from the two populations, in particular their ranks in the combined population. So, mathematically we can define rank for x observations and y observations in the following way. The rank of xi the ith x observation in the combined population is Rxy of xi. This is equal to summation over k is equal to 1 to m s xi minus xk, and summation over k is equal to 1 to n s xi minus yk, where s indicates a step function which is 0 if x is less than 0 and 1 if x is greater than equal to 0. Therefore, s function looks like this. It is 0 before 0, from 0 onwards it is 1. So, this is a type of step function that Sx denotes. In a similar way, the rank of an y observation yi can be defined as summation over k is equal to 1 to m s yi minus xk plus k is equal to 1 to n s of yi minus yk. So, this is the one for which we are trying to find the rank, and this we are subtracting all x values and y values, and based on that difference we are trying to calculate the rank. Let me illustrate with an example. Suppose my combined sample is 1.1, 2.2, 3.3 like up to 7.7. What is the rank of 5.5? So, it is an y observation. Let us assume that blacks are y's and x's are in red. So, its rank, as we can easily see, is 5. How to do that? So, we are subtracting all the observations from 5.5. Therefore, 5.5 minus 1.1, 5.5 minus 2.2, 5.5 minus 3.3 up to 5.5 minus 7.7. Quite naturally, these are all plus and this is 0 and these are minus. Therefore, S values is 1, 1, 1, 1, 1 and 0 here. So, how many ones are there? There are 5 ones. Therefore, rank of 5.5 is equal to 5. That in any case we have tabulated here. Another example, what is going to be the rank of 1.1? So, what we are doing, from 1.1 we are subtracting all the observations and all of them are minus except 0. So, in the S function we get only 1 1 and remaining all zeros. Therefore, rank of 1.1 is equal to 1. In this lecture, we prove some important results on the distribution properties of the linear rank statistic of the form Tnz is equal to sigma ai zi, and n is equal to m plus n. As I said earlier that we will be focusing on x observations. Therefore, zi is equal to 1 if ith observation in the combined population is an x, and it is 0 if ith observation in the combined population is an y. So, result 1, under the null hypothesis, that is both of them are from the same distribution, f x z is equal to f y z is equal to f z for all z. We have for all I is equal to 1 to n. Expected value of z I is equal to m by n. M is equal to number of x observations and n is total number of observations. Variance of z I is equal to m n upon n square, where n is equal to number of y observations. and covariance of Zi and Zj is equal to minus Mn upon n square into n minus 1, when j is different from I. Under the null hypothesis, Zi is a Bernoulli distribution or Bernoulli random variable, where success is considered when the ith random variable in the combined ordered sample is from x. I hope you understand it, but let us assume that these are the n ordered observations, out of which m of them are ones and n of them are 0, because these are coming from x and these are coming from y. Therefore, when we randomly pick up one value, probability Z I is equal to 1 is equal to m by n, and probability Z I is equal to 0 is equal to n by capital N. Therefore, it is similar to a coin tossing with P is equal to m by n. Therefore, each Z I can be thought of as a Bernoulli random variable with P is equal to m by n. This is what we have written here, that probability Z I is equal to 1 is m by n, probability Z I is equal to 0 is equal to n by n. Therefore, expected value of Z I is equal to 1 times probability Z I is equal to 1 plus 0 times probability Z I is equal to 0, and therefore, it is coming out to be 1 times m by n plus 0 times n by n is equal to m by n. Now, variance, we know that variance of a random variable x is equal to expected value of x square minus expected value of x whole square. So, let us first calculate expected value of Z I square. This is equal to 1 square times probability Z is equal to 1 plus 0 square times probability Z I is equal to 0, which is again coming out to be m by n. Therefore, variance of Z I is equal to m by n minus m square upon n square, which is equal to m n minus m square upon capital N square. If we take m common, it is capital N minus small m upon n square, and this quantity is nothing but small n. Therefore, m n upon capital N square is the variance of each Z I. So, these two results have been proved. Now, we need to prove that covariance of Z I Z j is equal to minus m n upon n square into n minus 1 when I not equal to j. We know that covariance of x y is equal to expected value of x y minus expected value of x times expected value of y. Therefore, when we are trying to compute covariance of Z I and Z j, this is going to be expected value of Z I Z j minus expected value of Z I times expected value of Z j. Now, expected value of Z I Z j is equal to 1 times probability Z I is equal to 1 and Zj is equal to 1. Why? Because Zi, Zj, the product is going to be 1 when both are 1, and this is going to be 0 if at least one of them is 0. Now, both Zi and Zj will be 1 if out of the m observations of x, one is at the ith position and one is at the jth position in the combined population. Therefore, the number of ways of choosing 2 out of m observations of x is MC2, and the total number of possible choices is capital NC2. Hence, probability Zi is equal to 1 and Zj is equal to 1 is MC2 upon capital NC2 is equal to m into m minus 1 by 2 upon n into n minus 1 by 2, which is equal to m into m minus 1 upon n into n minus 1. Therefore, expected value of Zi Zj is equal to m into m minus 1 upon n into n minus 1. Therefore, covariance of Zj, which is defined as expectation of Zi minus expected value of Zi into Zj minus expected value of Zj, is equal to expected value of Zj minus Zi times expected value of Zj minus Zj times expected value of Zi plus expected value of Zi times expected value of Zj, which comes out to be expected value of Zj minus Zi into m upon capital N, because for each z the expected value is small m upon capital N. Similarly, expected value of this is also m upon capital N, and both of them are giving me small m square upon capital N square. Now, by linearity of expectation, if this is equal to expected value of Zj minus m by n times expected value of Zi minus m by n times expected value of Zj plus m square upon n square. This we have already calculated. So, this is coming out to be m square upon capital N square with a minus sign. This is coming out to be m square upon capital N square with a minus sign plus m square upon capital N square, which is equal to m into m minus 1 upon n into n minus 1 minus m square upon n square. Let us now expand them. Therefore, we get in the denominator n square into n minus 1, numerator is coming out to be n into m minus 1 minus n minus 1 into m square. So, let us again open it. It is m square into capital N minus mn minus m square into capital N plus m square. So, these two cancel out. If I take minus common, we are left with capital N minus small m, and capital N is equal to m plus n. Therefore, n minus m is equal to small n, and therefore, we get the result. So, this is proved. In a similar way, let us prove another result, which is from conditional probability. What is the conditional probability that Zi is equal to 1 given Zj is equal to 1? We know that from the definition of conditional probability, probability Zi is equal to 1 given Zj is equal to 1 is equal to probability Zi is equal to 1 and Zj is equal to 1 divided by probability Zj is equal to 1, which is coming out to be m into m minus 1 upon capital N into capital N minus 1 multiplied by capital N upon small m, which is coming out to be m minus 1 upon n minus 1. Intuitively it is clear. If Zj is equal to 1 is given, implies that in the jth position there is an x. Therefore, Zi is equal to 1 can happen in how many ways? And x can be chosen out of small m minus 1 many remaining x's. Thus, we get m minus 1 in the numerator. In the denominator, it is very natural that out of the remaining capital N minus 1 observations, anyone can come there. Therefore, the probability is going to be small m minus 1 upon capital N minus 1. Try to prove the results. What is the probability Z I is equal to 1 given Z j is equal to 0 and probability Z I is equal to 0 given Z j is equal to 1 and probability Z I is equal to 0 given Z j is equal to 0. I leave this as an exercise for you. This is simple combinatorial problems, but you will be able to do it. Now, let us go to the result 2. Let T n is equal to sigma a I z I, where a 1, a 2, a n are constants, then under the null hypothesis, expected value of T n is equal to m times sigma I is equal to 1 to n a I upon capital N, and variance of T n is equal to m n upon n square into n minus 1 multiplied by n into sigma a I square minus sigma a I whole square. So, let us prove it. Expected value of T n is equal to m times sigma a I upon n. It is very straightforward, because T n is equal to a 1 times z 1 plus a 2 times z 2 plus a n times z n. Therefore, expected value of T n is equal to a 1 times expected value of z 1 plus a 2 times expected value of z 2 plus a n times expected value of z n. So, this is what we have written is equal to sigma I is equal to 1 to n a I times expected value of z I is equal to a I times m upon capital N summation over I is equal to 1 to n. If we take m to out of the summation, we get the result. It is a very straightforward thing, but what about variance? How do we show that variance of T n is equal to this complicated quantity? So, let us start. We know that variance of a x plus b y is equal to a square times variance of x plus b square times variance of y plus 2ab covariance of x and y. When we generalize it, we get variance of T n is equal to ai squared times variance of z I is equal to 1 to n, plus we are looking at all pairs and trying to find the covariance of z I and z j. This is equal to sigma ai square multiplied by mn upon n square. This we have already found that variance of z I is equal to this, plus the double summation a I a j multiplied by minus mn upon n square into n minus 1. This we have already found out. Therefore, this is coming out to be mn upon n square sigma a I square minus mn comes out of the summation. Therefore, we get double summation I and j, I not equal to j, a I a j divided by n square into n minus 1. Now, if we take mn upon n square into n minus 1 common, we have capital N minus 1 multiplied by sigma a I square minus this summation, double summation I is equal to 1 to n, j is equal to 1 to n, a I a j, j not equal to I. Now, we break it as n into sigma a I square minus sigma a I square minus this double summation. Now, we put this inside this summation. Therefore, what we are getting? N times sigma a I square minus sigma a I square and sigma sigma a I a j. This is nothing but sigma over a I whole square. Therefore, the whole thing boils down to mn into n square minus 1 multiplied by n into sigma a I square minus sigma a I whole square, and thus we get the result for variance. Now, let us revisit Wilcoxon rank sum test. We have found out that in the Wilcoxon rank sum test, the statistic is W, which is the sum of ranks of the x observations, and therefore, we have written it as sigma I z I. Therefore, expected value of W is equal to m into n plus 1 by 2 and variance of W is equal to mn into n plus 1 by 12. This we have stated in lecture 3. Now, let us prove it. Expected value of W is equal to m times sigma over I is equal to 1 to n a I upon n. This we have just found out. Now, replace a I with I, because that is the value of a I in this summation, that is a I. Therefore, we can write it as m times sigma over I 1 to n I upon capital N, and this is equal to, if I write one step further, m upon capital N into n plus 1 by 2, n gets cancelled and therefore, we get the result. In a similar way, what is going to be the variance? Now, variance of W is equal to this term that we have already calculated. Now, let us put the value of a I. Therefore, this boils down to mn upon n square into n minus 1 into n sigma I square minus sigma I whole square. Now, summation over first n natural integer square is equal to n into n plus 1 into 2n plus 1 by 6 minus n into n plus 1 by 2 whole square multiplied by this quantity. So, let us take out n square upon 12 from this. Therefore, we are left with 2 into n plus 1 into 2n plus 1 minus 3 into n plus 1 whole square, which is equal to mn upon n minus 1 into n plus 1 by 12, 2 into 2n plus 1 minus 3 into n plus 1 is equal to mn upon n minus 1 n plus 1 upon 12, 4n plus 2 minus 3n minus 3. This comes out to be n minus 1, which cancels with this. Therefore, we are left with mn into capital N plus 1 divided by 12. So, that is the variance of the Wilcoxon rank sum test statistic W. We have used the result, but we proved it today. Now, another important aspect of linear rank statistic is symmetricity. That means, whether it is symmetric around its mean value. That means, a statistic T is considered symmetric about its mean mu if for every k not equal to 0, probability T n z minus mu is equal to k is same as probability T n z minus mu is equal to minus k, or in other words, probability T n z is equal to mu plus k is equal to probability T n z is equal to mu minus k. So, that is what we call it symmetric. For illustration, consider T n z. So, suppose this is the distribution, this is the mean value of T n z, which we are calling mu. It is considered to be symmetric if the value at a distance k from mu is same as the value at a distance minus k. That is what we are saying here. Note that k need not be an integer. It can be any real value. If the null distribution of linear rank statistic is symmetric, the advantage is that we need to generate only half of the probabilities. As you can easily understand, if we know the probability density for this part, we know what is the density for the other half. So, that is why symmetric distribution is very useful many times. The question is how to check the above. How do you know whether a distribution is symmetric? We cannot check for all possible k. Therefore, we need to find a device. So, the intuitive idea is following. Suppose that corresponding to every vector z of m 1s and n zeros, there exists another vector z prime also of m 1s and n zeros, such that T n z is equal to mu plus k. Whenever that happens, that for z we get the value of T n z is equal to mu plus k, then for z prime the value of T n z prime is going to be mu minus k. That means what? For each case of mu plus k, there is a corresponding case of mu minus k. Therefore, number of cases for this is same as the number of cases for this, and therefore, their probabilities are also going to be the same. That is what we have written there. Then the frequency distribution of mu plus k is same as that of mu minus k, and therefore, the distribution is going to be symmetric. Thus, condition for symmetric can be modified as T n z plus T n z prime is equal to twice mu. So, whenever we get for each z another z prime such that T n z plus T n z prime is equal to twice mu, and that happens for all z, and therefore, we can say that the distribution of T n is symmetric. Now, there are several results available for that. So, we are stating some of the results which are simple relations which ensure symmetry when z and z prime are called conjugates. So, let us go to prove the result number 3. The null distribution of T n z is symmetric about its mean mu whenever the weight vector a I satisfies the following, that a I plus a n minus I plus 1 is equal to C for all I is equal to 1 to n, where C is a constant and mu is equal to, as you already know, is m by n into sigma a I. So, let us look at it very carefully. It is saying a I plus a n minus I plus 1 is equal to C. So, put I is equal to 1. So, therefore, it is saying a 1 plus a n is equal to C. Put I is equal to 2, it is saying a 2 plus a n minus 1 is equal to C. I is equal to 3 implies a 3 plus a n minus 2 is equal to C. Therefore, what we are saying is that if a 1, a 2, a 3, a 4, a n minus 3, a n minus 2, a n minus 1 and a n, if this is the A vector, then this plus this, this plus this, this plus this, this plus this, each such pair will have the same summation. Let us first prove the result. So, corresponding to each z of m 1s and n 0s, we define the conjugate vector z 1 prime, z 2 prime, z n prime also of m 1s and n 0s, where z I prime is equal to z n minus I plus 1. Therefore, if this is the z vector, z prime is going to be the reverse of that. That means, we look at it from this side. Therefore, if z is equal to 1 1 0 1 0, z prime is equal to 0 1 0 1 1. So, that is the basic property. In this case, T n z plus T n z prime is equal to sigma a I z I plus sigma a I times z n minus I plus 1, because z I prime is equal to z n minus I plus 1 is equal to sigma a I z I plus, now we are making a change of variable, we are calling n minus I plus 1 is equal to j. Therefore, z n minus I plus 1 becomes z j, and a I is equal to a n minus j plus 1, because I is equal to n minus j plus 1 is equal to a I plus a n minus I plus 1, I is equal to 1 to n times z I by change of variable j to I is equal to C times sigma z I is equal to C times m. Therefore, T n z plus T n z prime is a constant. So, We are through if we can show that Cm is equal to twice mu, because if you remember we said that distribution will be symmetric if Tnz plus Tnz prime is equal to twice mu. Now, expected value of Tnz is equal to m times sigma ai upon n is equal to mu. Similarly, expected value of Tnz prime is equal to m times sigma ai prime upon n is equal to mu, where ai prime is the constant we defined for z prime. Therefore, together we get Cm is equal to twice mu. Therefore, Tnz plus Tnz prime is equal to twice mu. Therefore, the condition for symmetry is met with, and therefore, Tn is symmetric. Proved. Let me now illustrate this with a simple example with m is equal to 3 and n is equal to 2. That means, we are looking at z vectors of 3 ones and 2 zeros, and the number of possible ways of doing it is 10, because this is factorial 5 upon factorial 3 factorial 2 is equal to 4 into 5 upon 2 is equal to 10. Therefore, we need to consider 10 permutations. That is what we have done: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let us consider the a vector to be this and a vector like this. Note that here the condition is not maintained that a I plus a n minus I plus 1 is constant, but in this case we can see that this is 2 plus 4, 5 plus 1 and 3 plus 3, all of them are going to be 6. So, in this case C is equal to 6. Now, if we calculate the value of Tnz, this is coming out to be, in this case, 6, 5, 4, 5, 6, 4, 7, 6, 5, 6. This you can easily calculate. For illustration, when it is 1, 1, 1, 0, 0, its dot product with 1, 2, 3, 2, 1 is going to be 1 plus 2 plus 3 is equal to 6. On the other hand, if I consider 0, 1, 1, 0, then its dot product is going to be 2 plus 3 plus 2, therefore, this is going to be 7. Therefore, what is going to be the distribution of Tnz? We can see that it takes the value of 4 2 times, 5 3 times, 6 4 times and 7 1 time, and the mean is coming out to be 5.4, because 6 plus 5 11 plus 4 15 plus 5 20 plus 6 26 30 37 43 48 plus 6 is equal to 54. Therefore, mean is equal to 5.4. In a similar way, you calculate for this a vector, you will find that our distribution is coming out to be 6 ones, 7 ones, 8 twice, 10 twice, 9 twice, 11 ones and 12 ones. Therefore, we can see that the mean of the distribution is coming out to be 9. C is equal to 6, we have already calculated. Therefore, twice mu is equal to 18 is equal to Cm, where C is equal to 6, m is equal to number of x is equal to 3. And we can see that this is symmetric around the mean. It is not a proof, because proof we have already given. This is only to visualize the result. Now, let me give you another result. The null distribution of Tnz is symmetric about its mean mu, which is equal to m into sigma ai upon n for any set of weights if m is equal to n is equal to capital N by 2. That is, if number of x is equal to number of y, then all Tnz's are symmetric. irrespective of the value of AIs. You consider any constants AIs, the distribution will remain symmetric provided number of x is equal to number of y. So, proof, note that m is equal to n. Therefore, let us define for on any vector z is equal to z1, z2, zn of m ones and n zeros, a conjugate vector also of m ones and n zeros as z prime is equal to z1 prime, z2 prime, zn prime, where zi prime is equal to 1 minus zi. That means, if in z the ith position is 1, then in z prime the ith position is 0 and vice versa. Because number of x is equal to number of y, that is m is equal to n. Therefore, by doing this transformation we still maintain the number of ones and zeros. Therefore, T n z plus T n z prime is equal to sigma a I z I plus sigma a I into 1 minus z I, because this is coming from z I prime, is equal to sigma a I z I plus sigma a I minus sigma a I z I is equal to sigma a I, because these two cancels. Now, mu is equal to m by n sigma a I. Now, small m is equal to n by 2 times sigma a I by n cancels. Therefore, we have half times sigma a I, implies that sigma a I is equal to twice mu. Therefore, T n z plus T n z prime is equal to twice mu. Therefore, by our condition of symmetricity, the null distribution of T n z is symmetric. So, illustration, we have taken simple case 2 m's and 2 n's. Therefore, capital N is equal to 4. We have chosen two arbitrary weight vectors 1, 3, 5, 4 and 3, 3, 7, 5. In this case, this is the distribution 1, 4, 1, 5, 1, 6, 1, 7, 1, 8 and 1, 9. Mu is equal to 6.5, and therefore, we can see that T n z plus T n z prime is equal to 2 into 6.5 is equal to 13, and as we can see here that 9 plus 4 is equal to 13, 7 plus 6 is equal to 13 and 8 plus 5 is equal to 13. Similarly, for case 2, the distribution will come out to be 6 once, 8 twice, 10 twice and 12 once. The mu is coming out to be 9, and we can see that T n plus T n z prime is equal to 12 plus 6 is equal to 18, 10 plus 8 is equal to 18 and 8 plus 10 is equal to 18. Therefore, we get that is equal to 2 times 9. Now, let me give you another result, which is the result number 5. This is the last result that we are going to do in this class. The null distribution of T n z is symmetric about its mean mu, which we know is m into summation I is equal to 1 to n a I upon n, if n is even and the weights are a I is equal to I for I less than equal to n by 2 and a I is equal to n minus I plus 1 for I greater than n by 2. That is, if the total number of observation is even and the weights given are a I is equal to I for the first half of the values and it is n minus I plus 1 for the other half of the values, then the distribution of T n is going to be symmetric about its mean. For a z satisfying the above, we define a conjugate z prime as follows: z prime I is equal to z I plus n by 2 for I less than equal to n by 2, and z I prime is equal to z I minus n by 2 for I greater than n by 2. So, let me illustrate with an example. Suppose n is equal to 8 and there are 4 ones and 4 zeros. So, consider a particular z which is 1 0 1 1 0 1 0 0. Therefore, how do you construct it conjugate z prime? For I is equal to 1 to n by 2, z I prime is z I plus n by 2. Therefore, z 1 prime is equal to 0 coming from here, z 2 prime is equal to 1 coming from here. Similarly, this is 3 from here and this is 4 from here. For I greater than n by 2, that means for 5, 6, 7, 8, the relationship is z I prime is getting the value of z I minus n by 2. Therefore, z 5 prime is getting the value of z 1, z 6 prime is getting the value of z 2, z 7 prime is getting the value of z 3, and z 8 prime is getting the value of z 4. So, like that, corresponding to each z, we can construct an appropriate z prime, and notice that this is also belonging to the same vector with 4 ones and 4 zeros. Now, therefore, the weights are going to be, it is a I is equal to I for I less than equal to n by 2. Therefore, for the first 4, the weights are 1, 2, 3, 4, and a I is equal to n minus I plus 1 for I greater than n by 2. Therefore, when I is equal to 5, it is 8 minus 5 plus 1, therefore 4. When I is equal to 6, it is 8 minus 6 plus 1, that is 3. Similarly, 2 and 1. Therefore, we can see that the weights are decreasing in a symmetric manner as well. We need to prove that T n is symmetric around its mean. So, let us prove it mathematically. T n z plus T n z prime is equal to sigma over I is equal to 1 to n by 2 I z I, and I is equal to n by 2 plus 1 to n, it is n minus I plus 1 z I. So, that is coming from T n z. In a similar way, T n z prime is equal to I is equal to 1 to n by 2 z n by 2 plus I, because that is how the z prime has been allocated values, and for I is equal to n by 2 plus 1 to n, it is n minus I plus 1 into z I minus n by 2 is equal to, for I is equal to 1 to n by 2 I z I plus I is equal to n by 2 plus 1, it is n minus I plus 1 z I. Now, here what we are doing? We are making a change of variable. So, on this side we make a change of variable, n by 2 plus I is equal to j. Therefore, I is equal to j minus n by 2. Therefore, what we are doing? We are putting instead of I j minus n by 2, and in place of n by 2 plus I, we are putting j, and since I is going from 1 to n by 2, j is going from n by 2 plus 1 to n. In a similar way, we are again making a change of variable, and what we are getting is that j is equal to 1 to n by 2, it is n by 2 minus j plus 1 multiplied by z j, which is equal to sigma I is equal to 1 to n by 2 I z I plus j is equal to 1 to n by 2 n by 2 minus j plus 1 z j. That is, we are combining this and this. In a similar way, we combine these two and therefore, we get this following: I is equal to n by 2 plus 1 to n minus I plus 1 z I plus j is equal to n by 2 plus 1 to n j minus n by 2 z j. Here we can make a change of variable. Instead of j, if I call it I, then what we are getting I z I plus n by 2 minus I plus 1 z I, and when we combine them, I and minus I cancels, therefore, we get n by 2 plus 1 times z I is equal to 1 to n by 2. In a similar way, when I am calling it instead of j equal to, we call it I, then we will get that it is I is equal to n by 2 plus 1 to n by 2 plus 1 to n. Now, this cancels with this, therefore, we get n minus n by 2 is equal to n by 2 plus 1 times z I. So, together what we are getting? Together we are getting it is that sigma I is equal to 1 to n by 2 plus 1 times z I. Now, we can take it out of the summation, and sigma z I is equal to 1 to n is equal to m. Therefore, what we are getting is twice mu. Therefore, it is symmetric. With this background, we look at the mood test. In the mood test, the statistic is m n is equal to I is equal to 1 to n I minus n plus 1 by 2 whole square times z I, where z I is equal to 1 if ith rank corresponding to an x sample. That means, we are looking at the ranks of x values. We want to show that expected value of m n is equal to m into n square minus 1 by 12, variance of m n is equal to m n into n plus 1 into n square minus 4 by 180, and if m is equal to n and both are equal to n by 2, then the null distribution of m n is symmetric about the mean. So, let us prove the first result. Expected value of m n is equal to m summation a I over n, this we all know, is equal to this m n into sigma a I is equal to m by n sigma I is equal to 1 to n I minus n plus 1 by 2 whole square is equal to m by n multiplied by summation of I square minus 2 into n plus 1 by 2 times I plus n plus 1 by 2 whole square by opening up this square is equal to m by n times sigma I square minus n plus 1 times sigma I plus n plus 1 by 2 whole square times sigma 1, because there is no variable involved, is equal to n into n plus 1 into 2 n plus 1 by 6 minus n plus 1 times n into n plus 1 by 2 summation over I plus n plus 1 by 2 whole square times n. This is straightforward. Now, let us simplify it, is equal to n into n plus 1 into 2 n plus 1 by 6 minus n into n plus 1 whole square by 2 plus n into n plus 1 whole square by 4 is equal to, the first term comes as it is, these two gives us minus n into n plus 1 whole square by 4. Therefore, as we simplify it, we take out n into n plus 1 by 12 common, what we get is 2 into 2 n plus 1 minus 3 into n plus 1, which is further simplified as 4 n plus 2 minus 3, which is equal to n minus 1. Therefore, the expected value comes out to be m into n square minus 1 by 12. In a similar way, one can compute the variance of m n is mn into n plus 1 into n square minus 4 by 180. One has to go and expand it in this following way by putting the value of a I, but as you can understand that it is very laborious arithmetic. I am leaving it as an exercise for you. You please try and check that actually you could arrive at this value for the variance. The third one was that if m is equal to n, then the null distribution of m n is symmetric about the mean. This already we have proved that for equality of m n, all the linear statistics are going to be symmetric, therefore, it comes naturally. Okay, friends, I stop here today. In the next class, I shall describe a few tests on goodness of fit. Thank you very much.